broken. So again, that would be clarified. So we're going to fill in the neutral here as if it wasn't broken. Now we can start to figure out what the resistive values are. That's a first step in solving a neutral, broken neutral question. You want to know what these resistive values are for each load. Because the resistive values aren't going to change even after the neutral breaks. Again, they're engineered into the particular device that you have hooked up, whether it's a light bulb or a motor, what have you. So we know our current values, and we also know that between line 1 and line 2, because it's hooked directly in between line 1 and the neutral, we're going to see 120 volts across there. Likewise, load 2 is connected between line 1 and neutral directly, so we have 120 volts across there. And same with load 3, this time between line 2 and neutral, and same with load 4. Alright, let's change up our color here and solve for the resistance. So because we know the voltage and the current, we can now figure out what the resistive values for each load is. So 120 divided by 14 will give us load 1, which is 8.75. Or sorry, 8.57. Load 2 is going to be 120 divided by 4, which is 30. Load 4 is 120 divided by 9, giving us 13.3 ohms. And load 3 is 120 divided by 5, which is 24 ohms. Okay, so now we know what our resistive values of each load. Now the neutral breaks, and we can disregard all our voltage drops as well as our currents. So we'll erase that conductor or neutral. It's out of the equation, as well as our voltage drops. They're going to change. Our current is now changing, but our resistance remains the same. So let's get rid of that neutral. It no longer exists if there's a break in it. So we'll all but get rid of it. Likewise, these current values can be disregarded. So now our circuit looks something like this here. Also, our source voltage, our 120, because we don't have the neutral splitting the 120 volts and 120 volts, it is going to be now between line 1 and line 2, 240 volts. So this circuit here is a combination circuit. Now, a pretty simple combination circuit, although this line tends to mix a lot of people up here, this one. So I'm going to scroll down here and just redraw the circuit in a manner where I find it a little bit easier to interpret it. Alright, so the circuit above can match or is the exact same as the circuit that I'm drawing. you'll see that line 1 and line 2 are connected to, or load 1 and load 2 are connected to line 1, just like up here. They're connected to line 1. Same with here. And load 1 and load 2, they're both connected to load 2, or 3 and 4. And then 3 and 4 up here go back to the source. 3 and 4 also go back to the source. So it's just a different way of drawing out the circuit, which I find a little bit easier to interpret. So I can translate now my resistive values from above onto the circuit here. So we got 8.57 ohms in parallel with 30, 24 ohms in parallel with 13.3 ohms. All right. So what I want to boil the circuit down to is I already have my voltage total. It's 240. I also want to find my resistance total, my current total. So I have all my resistor values, but I just got to figure out what the total resistance is. So I got to simplify this combination circuit now. And the first step I'm going to do is to turn these parallel resistors and this parallel resistor into one equivalent resistor. So I'm going to once again redraw my circuit. Got 240 volts into two resistors in series. So I got to figure out what the equivalent resistance is of those two resistors, and I can use the product sum method. So the 8.57 multiplied by 30 over 8.57 plus 30. And that's going to give me the value of my equivalent resistance. So 8.57 multiplied by 30 divided by 8.57 plus 30 equals, so 6.67 ohms. And likewise, 24 multiplied by 13.3 over 24 plus 13.3. So I'll calculate that. And I get 8.56. Now, just as a reminder, I can also solve it using the reciprocal adding method. So 1 RT is equal to 1 over 24 plus 1 over 13.3. So if I were to calculate that, I also get 8.55 or 8.56 ohms. Okay, so now I just got to simply add those together, and that'll give me my total resistance for the circuit. So I have 15.2, a resistance of 15.2 ohms for the entire circuit. All right, now I can figure out what my current is by dividing voltage or resistance into the voltage. So 120 divided by my answer, it's going to give me 7.88 amps. All right, let's change up the color here. Okay. So I have 7.88 amps going through this resistor here, and this is going to allow me, both of my resistors, this is going to allow me to find my voltage drop going through each of these equivalent resistors. So I have 52.6 volts on this resistor, and if I go 8.56 times 7.88, get 67. Oh, I must have made a mistake here. With where did I make a mistake? Added that together, that's my total resistance. Let's try current again. So 240 divided by 15.2. Oh, I made a mistake with my current. So the reason I figured I made that mistake, if I multiply 8.56 times 7.88, I get 67.5 volts. And my 67.5 volts and 52.6 volts, they do not add up to my source. So I knew there that I must have made a mistake somewhere along the lines. So it's always a good idea to kind of double check your answer by calculating it in a different method. So go back here to where I found my total resistance. 240 divided by 15.2 gives me 15.8 amps going through the circuit. Not sure how I got that wrong, but let's now add that into our series circuit here to figure out the individual voltage drops of each of those equivalent resistors. So now that I have resistance and current, I can figure out the voltage drop. So 15.8 multiplied by 6.67 gives me 100. Let's change the color. 105 volt drop, and 8.56 times 15.8 is 135 volts. All right, so 135 plus 105 gives me my 240 volts. So now I'm happy, I'm satisfied with that. Now what we got to do here is, because my voltage drop across this equivalent resistor is 105, well, I can go back up to my expanded out circuit, and I know that the voltage across parallel resistors are going to be the same, so I can take that voltage and that's going to be my drop across both those resistors up there. Likewise, my equivalent resistor here, voltage drop of 135, and I can apply that. To those resistors. So having a good background in being able to solve combination circuits is pretty key to figuring this question out. All right, so I have my voltage drops there, so I'm gonna add it to my original question up here. So 135 volts, 135 volts, 105 volt, 105. So now I could, if I wanted to, I could figure out my current going through those as well. line 1, line 2, and line 3. So for the heck of it, let's do that. So 135 divided by 24, I have 5.63 amps. 135 divided by 13.3, I have 10.1 amp, we'll call it 10.2 amps. 105 divided by so 105 divided by 30, it's going to give me 3.5 amps through load 2, and 105 divided by 8.57, it's going to give me 12.3 amps going through that load there. Alright, so if it asks for that in a particular question, we're able to solve for the current going through each of those loads now. Now, one other thing it might ask you for is the voltage drop across the neutral. So let's bring back the neutral into this particular circuit, and let's try to figure out what the voltage drop would be across that neutral. So with our neutral intact, we have no current going through the neutral because it's broken, but we do have a potential difference between one side of it and the other side, like kind of like pressure. There's potential difference but no current flow. All right, so what we want to do is we can trace our 120 volt is going to be our source here, and our drops across any one of our loops back to the source has to equal 120 as well. So from this point here to this point here, no matter where I trace, has to also be 120 volts. So let's say I just trace this shortest path here. Well, I have 105 volts here, which obviously doesn't equal 120. So I must have the difference between each point of that neutral. So I must have a 15 volt drop across the neutral. Likewise, if I traced this way across line 2 and load 3, well, I have 120 volts to start with and 135 volts across load 3. So those need to match, so I have a potential difference of 15 volts, again, between 135 and 120 volts. So a potential difference of 15 volts on the neutral is again confirmed. So that's how you solve that particular question.